Did you like how I played my Wordle? Or did that make you mad? I hope you were mad, because Wordle is not played like that if you're playing to win. But what would have been better? It would have been better if I had used my previous knowledge and built off of that. And why did I play so ridiculously in the beginning? Because that's how traditional Greybox fuzzers work today. But first, forget Greybox. What's a fuzzer? Okay, so you're a software developer and you're writing code, and like any good developer, you are testing the code. But then you need to generate more test cases than you can fathom. So what do? Do you despair or fall into a state of anguish? No. You write a fuzzer. A fuzzer is something that helps you test your code by automating the process of generating test cases, aka input, aka seeds. This helps you find vulnerabilities in your code without losing time or wasting energy. Now that you know all that, how does a traditional Greybox fuzzer work? So it takes those inputs or those test cases and applies small mutations to them, usually at a byte level, like flipping bits or changing characters. Then it runs the program using these mutated inputs and observes what happens, and specifically which parts of the code get executed. This is what we call coverage information, code coverage. Now, here's the key step. If a mutated input causes the program to reach new code that hasn't been seen before, it's considered interesting. The fuzzer saves that input and that specific test case and adds it to a queue. And instead of continuing to mutate the original inputs, it now starts mutating these more interesting ones. So over time, it keeps building on those inputs that explore newer parts of the program, repeating this process again and again. So at a high level, this system is already using feedback, but it doesn't use it precisely. More on that later. You know what a fuzzer is, you know what a Greybox fuzzer is, and now I'm going to give you a high-level overview of the popular Greybox fuzzer American Fuzzy Loft, or AFL for short. AFL mutates the test cases that you put into it in two main stages. In the deterministic stage, AFL goes through the input one position at a time and applies small, predefined changes. For example, it might flip a bit, change a byte, or try simple value modifications. These mutations are applied in a systematic way, so AFL can carefully test small variations of the input. After this, AFL moves to the havoc stage. In this phase, mutations become much more random. Instead of making one control change at a time, AFL performs a random number of mutations in sequence. It randomly chooses both the type of mutation and the position in the input. This allows the fuzzer to make larger and more unpredictable changes, which can sometimes jump to entirely new parts of the program. If the test case or input managed is interesting, which means it reaches new code, then they keep that test case. The concept of building on interesting inputs intuitively makes sense. If we build off of our test cases that increase code coverage, aren't we closer to finding bugs? Yes, but there is a problem in Greybox fuzzing. The mutations done to these interesting inputs are done at random. Let us say that you have the test case ABC'3582. Now, because it starts in ABC, it can pass this first branch. And because the number 3582 is greater than 3000, it passes this second branch. And it's increased code coverage, so now it's marked as interesting. In the next step, we're going to mutate it to get our second input. And the mutation of the seed results in FGQ1283. Now, while this maintains some of the previous seed, it doesn't increase code coverage or reach the branch that our first test case increased. We move on. This is exactly what the issue was with our Wordle problem. We had hints, but we weren't using that information to build our next guess. This problem, while seemingly small, can grow exponentially worse when we are dealing with large-scale testing. The mutation didn't increase reach to parts of code untouched, so that code isn't tested. Even though AFL keeps inputs that improve coverage, it doesn't preserve why they were successful. Coverage drives bug discovery. If a fuzzer doesn't reach certain parts of code, it simply cannot find bugs in those regions. And in practice, as the paper suggests, tools like AFL often fail to explore large portions of a program. This means that important functionality and potential vulnerabilities can remain completely untested. We are foregoing the hints that Wordle gives us and randomly guessing, even though it doesn't help us get to our answer.
The paper that I used for my research directly addresses this problem. This paper is called FairFuzz, a targeted mutation strategy for increasing Greybox fuzz testing coverage. This paper introduces FairFuzz, a technique that augments AFL fuzz testing by making better use of feedback. It was introduced by Caroline Lemieux and Kushik Sen from UC Berkeley.
Instead of treating all inputs equally and mutating them randomly, FairFuzz focuses on two key steps. One is identifying underexplored parts of the program through finding something that they call rare branches. And two is preserving the parts of interesting inputs that help reach those areas through something called mutation masking, so that new inputs are more likely to hit those rare branches again, and exploring deeper into the program. From our previous example, if ASE'18 got us to a deeper part of the code, we keep the input parts that led us to that branch and mutate the rest. And again, both of these ideas are driven by code coverage. FairFuzz tries to generate better inputs instead of just generating more inputs. So the first step that we were going to talk about for FairFuzz is rare branches. But first of all, what is a branch? That's important to understand in both FairFuzz and AFL. So a branch is essentially a decision point, like an if statement, where the program can take different paths depending on the input. For example, if a condition is true, the program might execute one block of code, and if it's false, it will take another path. Each of these possible paths is what we refer to as a branch. When AFL runs an input, it doesn't just check whether the program crashes, it'll also keep track of how the program executed, including which of these branches were taken. To do this tracking, AFL lightly instruments the program so it can observe how execution flows between different parts of the code. And so at a low level, the program can be broken into small chunks of execution called basic blocks, which are essentially just straight line pieces of code with no branching inside them. And so AFL assigns each of these blocks a unique ID, which is basically a random number. And AFL tracks transitions between them, meaning how execution moves from one block to another. So let's say you have a program with code blocks A, B, and C. AFL will create a unique ID for each transition. So the value that uniquely represents the transition from A to B will be different from the value that represents the transition from B to A. And similarly, if we do the same for A to C, we get a completely different value. So even though both transitions would start from A, they would be encoded completely differently.
Each time an input runs, AFL records which branches were exercised and how often, through a pair that uses encoded branch IDs and a hit count. This information leads us to our first step in FairFuzz, the rare branches. This is important because it's how FairFuzz uses this feedback to decide which inputs are worth keeping and pursuing. Any new pair of branch ID and branch hit is considered new coverage. So over time, AFL builds up a collection of inputs that each uncover something new about the program's behavior. And using this same information, we can start to see a pattern. Some branches are exercised over and over again, while others are barely reached at all. And this brings us to the idea of rare branches. During fuzzing, every input requires certain branches of the program. Over time, some branches are hit very frequently, while others are rarely reached. FairFuzz keeps track of how often each branch is executed and specifically focuses on the ones that are hit the least. Only those inputs are kept and added to the queue for further mutation. These rare branches are especially important because they often guard deeper, more complex, and less explored functionality in the program. In FairFuzz, these rare branches effectively become the target that we're trying to preserve during mutation.
The second step in FairFuzz is called mutation masking, and the goal is to identify which parts of an input are critical for reaching a specific rare branch, and then avoid modifying those parts during mutation. And before we dive into mutation masking and these changes, I want to dive into what a mutation is in this context. And so a mutation is just essentially a small change to the input or the test case. So things like deleting parts of the input, overwriting bytes, adding bytes. And when we talk about controlling mutations, we're really talking about controlling where and how these kinds of changes are applied. Now it's time to talk about the star of the show in FairFuzz, which is the mutation mask. For a given input that reaches a specific rare branch from the first step, FairFuzz looks at each position I in the input or test case one at a time. It tries different types of mutations, such as overwriting a byte, inserting a byte, or deleting a byte at that exact position, and after applying each mutation at position I, the program is re-executed to check whether the mutated input still reaches that same target rare branch. If a particular mutation at position I causes the program to no longer hit that branch, then that mutation is considered unsafe at that position. FairFuzz then builds a mutation mask, where for each position I, it records which mutation types, if any, overwrite, insert, or delete, are allowed, so that it can preserve the ability to reach the target branch. Now, FairFuzz can guide mutations much more carefully, preserving the structure needed to reach rare branches while still exploring newer variations in test cases. The mutation masking idea applies to both types of mutations that AFL algorithm performs, the more structured step-by-step mutations, or the deterministic phase, and the fully random ones, the havoc phase. And in the structured phase, FairFuzz checks each possible mutation before applying it. If a mutation would break the ability to reach the target branch, it simply skips it. So this is where the mutation mask is being created. And in the random mutation phase, often called the havoc stage, AFL would normally pick any position in the input completely at random. But FairFuzz changes this by only choosing the positions that are considered safe according to the mutation mask. So even when mutations are random, they're still constrained to parts of the input that won't destroy the progress we've already made. It has to adhere to the mutation mask. We've talked about rare branches and we've talked about mutation masking, and this essentially is all that it takes for FairFuzz. And putting it all together, FairFuzz selects inputs that already reach rare branches, identifies which parts of those inputs are critical, and then carefully, after creating a mutation mask, mutates only the parts that won't break that progress. This allows it to consistently generate new inputs or test cases that stay close to the target, while still exploring new variations of test cases, as I said before. Now, going back to the earlier analogy, it's like keeping the correct letters in Wordle and only changing the ones that are still unknown or wrong. This allows the fuzzer to build on partial progress instead of constantly starting over. After understanding how FairFuzz works, the next question is whether these algorithmic changes translate into measurable improvements in practice. And in this evaluation done in the paper, FairFuzz is compared against 3 widely used versions of AFL. The first baseline is the vanilla AFL, which is basically the standard implementation available from the AFL website. This serves as basically a reference or control. The second variant is called fidgety AFL, and this version disables AFL's deterministic mutation stage, so that first stage that we see in normal AFL. It just skips it and entirely relies on only the random or havoc mutations. This generally makes it faster and more aggressive in mutations. And the third variant is AFL fast.new, which, like FairFuzz, tries to prioritize rare paths in target code, but doesn't do any of the mutation masking that we see in FairFuzz, and TCP dump and other utilities that parse structured input formats. And they're mature real-world programs with complex control flow and input constraints. They make a direct impact on the software engineering industry. And so it's important and very essential that we find vulnerabilities. And if that process is facilitated by using fuzzers, then AFL and FairFuzz is a great way to go. So these graphs basically represent the AFL variants and how they performed for each benchmark over time. And the x-axis represents time, so up to 24 hours, because there were 24 hours per trial, and the y-axis represents the cumulative branch coverage, and each line corresponds to different fuzzing strategies in each benchmark. And so what I found particularly interesting is how the curves are behaving. And in several benchmarks, FairFuzz's curve rises more steeply in the earlier phases, which indicates that it reaches deeper logic faster. and in other cases, the improvement appears later into the run, and suggesting that kind of suggests that mutation masking helps unlock harder to reach branches over time. And this indicates that FairFuzz might improve both short-term exploration efficiency and long-term depth, as the authors suggested. As the graphs from these experiments showed you, across benchmarks, FairFuzz consistently achieves higher branch coverage than standard AFL, and in some cases, the variance of AFL. On average, the improvement in branch coverage is approximately 6% after the first hour of fuzzing and approaches 10% after 24 hours on certain programs. And each additional percent of coverage can correspond to entirely new control flow regions being explored, regions that may contain previously unreachable bugs.
To better understand how mutation masking affects exploration in the real world, the authors take a closer look at a specific example from XMLint benchmark, which is basically an XML parser. And so in this program, reaching certain deeper parsing logic requires constructing the XML keyword @list. And this keyword acts as a kind of gatekeeper, and unless the input contains this structured sequence, this program will never execute the deeper branch guarded by it. So Table 1 shows how many of the 24-hour runs for each fuzzing technique were able to generate inputs containing progressively longer prefixes of that word, such as A, AT, ATT. What's important here is not just whether the full keyword was discovered, but also how often the intermediate prefixes were successfully extended, because they build off of each other. And while several techniques could randomly discover the short prefix A, the number of runs that sharply decrease for longer prefixes in AFL and AFL fast. FairFuzz, however, produces the longer prefix AT in significantly more runs. This demonstrates that once FairFuzz discovers part of a structured sequence, it's more likely to preserve it and extend it further. In contrast, random mutation frequently breaks partially correct prefixes before they can grow in future test cases. So this table provides concrete evidence that mutation masking helps FairFuzz gradually build structured inputs that unlock deeper code.
That being said, the results also highlight some limitations. FairFuzz can only target branches that have already been hit at least once, so it still depends on some initial exploration. And in programs where progress doesn't provide intermediate feedback, its advantages are more limited. Another limitation is that this program works best in situations where target code is structured in a nested format. As seen in one benchmark where FairFuzz underperformed, recursive and other structures are difficult for this tool to work in. For example, a benchmark that FairFuzz underperformed in was C++Built. The input is not made up of long structured prefixes. And in C++Built, many branches depend on specific characters appearing at very precise positions. And small mutations can easily invalidate the symbol encoding, and so because of this, rare branches may only be reachable by very specific full strings and not partial structures. The mutation mask may over-constrain mutation, preventing the exploration of necessary changes. On the other hand, there are some advantages of FairFuzz. You can combine it with other fuzzing techniques to generally increase code coverage and chance of finding new bugs. Another advantage is that it's also general. The masking mechanism doesn't require any knowledge of the input format.
So overall, the evaluation shows that a relatively simple idea, preserving useful parts of inputs and focusing on rare branches, can lead to meaningful improvements in how effectively we explore programs. And this brings us to the question, who cares? In short, we do. The longer answer is that fuzzing itself is a major bottleneck in software security. Modern software systems, as you may know, are enormous, and fuzzing is a widely used automated technique for discovering bugs before attackers do. But even powerful fuzzers like AFL can get stuck. They can spend hours exploring the same well-traveled parts of a program, while entire parts of code remain untouched. FairFuzz tries to address that exact problem by focusing the search on rare branches, the parts of the program that very few inputs ever reach. And these rare branches are often where the most interesting behavior lives. If we bring this back to the Wordle analogy we started with, The early guesses are easy. Lots of words will fill a few letters. But as you narrow things down, the final letters are much harder to discover. They require using the clues you already have and carefully refining your guesses. Rare branches in a program are like those final letters in Wordle. They're the hardest parts to reach, but they're also the ones that matter the most. FairFuzz essentially makes the fuzzer play Wordle more intelligently, preserving the letters that are already correct and focusing the search on the positions that are still unknown.